Hi everyone, and welcome to this Key Stage 3 Science video. What we're going to do in this video is a review of some Key Stage 3 chemistry exam questions. So the first time I show a question, it will be blank, and that means that if you haven't had a chance to look at these particular questions before, you can pause the video and have a go at the question before I do a walkthrough of how to answer them. Just so you are aware, when I'm answering these questions, I will be writing down my thoughts or my observations in yellow. So these are to help you understand the questions. They're not going to gain me any marks. My actual answers will be in green. And if there are two possible answers, I will write both of them, but I'll tell you if you only need to write one. So pause this now if you want to have a go at these questions. Now this question and a lot of the other questions are about experiments. So let's have a read. Ruth puts a piece of a different metal in each of 4 test tubes. She poured 10 cubic centimetres of hydrochloric acid onto each metal. And we can see the metals now. We've got iron, we've got zinc, we've got magnesium, and we've got copper. And into each one we have put hydrochloric acid. Look at the diagrams above. How do these show if a metal reacts with acid? And so this is very much say what you see. And what we see here is the piece of copper looks like it is doing nothing because it's just sitting there. The piece of magnesium is making lots and lots of bubbles. And so in the zinc, we have got some bubbles, but we've definitely got fewer bubbles than in the magnesium, and last of all the iron, we've got very few bubbles. Now look at the diagram above. How do these show if a metal reacts with the acid? Well, the answer is all to do with those bubbles. So we could put the fact that we are seeing bubbles, we could put the fact that it is fizzing. A fancy word for fizzing is effervescence. If you fancied using that show-off word there, that's a brilliant science word, effervescence. Or you could quite simply say that gas is given off. My favourite one is the effervescence, but my second choice would be the bubbling, rather than saying the gas is given off. And then the next question says, on the lines below, put the 4 metals, so we have to do all of them, in order of how strongly they react with the acid. And so the most reactive one is the one that reacted the strongest, and that one was the magnesium. We saw the greatest number of bubbles for the magnesium. Then second on the list was the zinc, because there wasn't as many bubbles, but there were still some. Iron gave a few bubbles, and last of all the copper, because copper did not do anything. Moving on to the next question. Choose the name of a metal from the box, so we're not just making this up, we've got 4 to pick from to answer each question. Which metal from the box is used for electrical wires? And the answer for that one is copper. Copper is used in electrical wiring. It is a really good conductor of electricity. Which metal from the box goes rusty? And that is iron. The rusty orange colour is iron combined with oxygen. This next question is about a different chemical reaction. This time iron filings, so that is a metal, are being added to copper sulfate solution. And she's observing this reaction over the course of 1 week, so that's quite a long time that she's leaving it for. And before the iron has been added, the iron filings are grey and the copper sulfate is a blue solution. So that means that in here this is blue. Then she's left it for 1 week, and after it's been left for a week, the solution has gone green. And then there is, at the bottom of the tube, there is a grey metal, but there's also some orange metal as well. And so what evidence in the diagram shows that a chemical reaction has taken place? Well, the answer is that there has been a colour change. And that's to the solution. So that's the colour change in the solution. And also, the second piece of evidence, we only need to put 1 because it's 1 mark. The second piece of evidence could be that we have made a new metal. So this is a possible answer as well. So made a new metal. For part B, it says that the reaction between iron and copper sulfate is a displacement reaction. And that's where one metal takes the place of another. And so at the beginning of this reaction, the particles of the metal iron are by themselves, and copper metal is connected to the sulfate in a compound, copper sulfate. But what happens is one metal, the iron, takes the place of the copper. And so the copper is left by itself because the sulfate that it had before has been taken from it by the iron, and the iron is joined to it in iron sulfate. So in terms of these questions, part 1 here, give the name of the orange metal visible. Well, the answer is copper, because copper is an orange metal. What is the name of the compound formed? Well, that's the other chemical, the iron sulfate. And it's a compound because there is more than one element present. There's iron, there's sulfur, and in fact there's oxygen as well. The next question. Joanne poured the green solution into another tube. She added some copper pieces to the solution. Will a displacement reaction occur? Well, effectively, what she's trying to do is she's trying to reverse what happened in the previous question, and she's trying to see if copper will take the place of the iron. Now, the answer is no, nothing is going to happen. And the reason for that reaction is that iron is more reactive than copper. Or you could also say that copper is less reactive than iron. And so what that means is, in the displacement reaction, if copper tries to come along and steal the sulfate back from the iron, it can't do it because iron is more reactive. So the copper is trying to take it away, but iron is too strong and it holds on to it because it is more reactive. Then we've got a different parts of the reactivity series here in C. We've got the most reactive at the top, and that's typically how you show it, and the most reactive is potassium, and the least reactive from this section is the lead. So use the information above. Which two metals would react with aluminium nitrate in a displacement reaction? And so the metals have to be able to react and take something away from aluminium, and aluminium is here. And so the three metals that are more reactive than aluminium are potassium, lithium, and calcium. And so if we find them, we've got potassium and we've got calcium in the top row. Zinc and lead, they are not reactive, so they won't be able to take any of the nitrate away from the aluminium. And so we need both of them for 1 mark because it says which two. This question is about particles. And so we've got methane can be a gas, a liquid, or a solid. In the diagram below, arrows P, Q, R, and S represent changes of state. And so that is to do with melting, evaporating, condensing, etc. The boxes show the arrangement of particles in 3 different states. Each circle represents a particle of methane. So we've got different physical states, and the physical states are solid or liquid or gas. That's what this means. So those are the different states, solid or liquid or gas. And so our command is to draw a line from each physical state of methane to the arrangement of particles. So draw only 3 lines. And so what we've got here is we've got lovely layers and we've got no spaces at all. And those are characteristics of a solid. And down at the bottom, we've got loads of space and we've got no symmetry at all. And so this is for a gas. And the one that's probably hardest to define is, therefore, in the middle, the liquid. So the particles are really close together. There's hardly any spaces, and liquids can't be squashed together, really. But there's not very much order to them. And so that's how we can tell a liquid from a solid. Arrows P, Q, R, and S represent those changes of state that I was mentioning earlier. Which arrow represents evaporation? Now, evaporation is, think about a puddle. That's where you have a liquid and then it turns into a gas. And so we now need to go up to here and we find out that one is arrow P. 1 mark for that. Which one represents melting? Think about an ice cube. A lump of ice is a solid and it melts and turns into a liquid. So we're looking for changing a solid into a liquid, and that is R. Sticking with particles, methane is the main compound in natural gas. The scale below shows the melting point and the boiling point of methane. Now the boiling point is the temperature that something boils at, and so that means it's the temperature where a liquid turns into a gas. And the melting point is the temperature that something melts at, and that's where a solid turns into a liquid. And we've got a number line here that's negative. Watch out for the fact that this is a negative number line, and in fact we only go up to 0, which is the normal freezing point of water, but methane's temperatures are all below 0. Methane has 3 physical states: solid, liquid and gas. What is the physical state at minus 170 degrees C? So we have to find that. That's minus 160 is here and minus 180 is here, so minus 170 is between the two, like that. Now remember that the melting point is a temperature that something turns into a liquid from a solid. So colder than the melting point, it will be a solid. Above the melting point, it will have melted and turned into a liquid. And then above the boiling point, it will have turned into a gas. And so because minus 170 is between the melting point and the boiling point, it will be a liquid. Now the formula of methane is CH4. The symbols for the two elements in methane are C and H. Give the names of these two elements. Well, C is for carbon and H is for hydrogen. When methane burns, it reacts with oxygen. One of the products is water, H2O. Give the name of the other product. Now the name is carbon dioxide. And that forms when the oxygen combines with the carbon to make carbon dioxide. But you could actually have another compound. You could have carbon monoxide as an alternative answer. You only need to put one of them, but you could have carbon monoxide, or last of all, you could just have soot or carbon. And that's what makes a flame smoky, because sometimes bits of carbon just get produced by the flame itself. So you could have either of those. You don't need all three. This next question is about burning. And the exhausts of a car, so that's the exhaust is the bit that comes out of the back. So if this is a very rubbish car, here's the car, and we've got the exhaust at the back, and that is the exhaust where all the smoke and the other gases get ejected. Now, it's analysed in an MOT test, and the results are shown below. The MOT test is just how you test to see whether something is roadworthy, whether the car is safe and not polluting too much. And so here are the different gases that get released by the car's exhaust. So most of it is just other, and we don't know what that means. Carbon dioxide is the highest one that's named at 13%. Carbon monoxide that I've just mentioned is 3%, and oxygen is the smallest percentage at 0.4%. The air going into the engine contains 20% oxygen. Explain why there is only 0.4% of oxygen in the exhaust gases coming out of the engine. And so in the engine, petrol is burnt and oxygen supports burning. And so oxygen is used up in burning, or you could say that it has reacted with the petrol or the fuel. I would prefer it if you didn't say that oxygen burns, because actually oxygen just helps things to burn. In question B, petrol is a mixture of compounds which contain only carbon and hydrogen. Complete combustion of petrol produces carbon dioxide and one other substance. What is that other substance? Well, actually, we had that in the previous question, and that is water. And that comes from the hydrogen combining with oxygen to produce water. And water is H2O, as we know, so oxygen is adding to the hydrogen. And then the final part of this question, when petrol is burned in the car engine, carbon monoxide is produced as well as carbon dioxide. Explain why carbon monoxide is dangerous and may kill you. Well, in fact, just quite simply, carbon monoxide is poisonous. And so what it does is it stops our blood being able to carry oxygen around, and so it ends up poisoning us and our brain can't function in the low oxygen levels. This final question is about bath bombs, and bath bombs, in case you didn't know, you drop them into a bath and they make the water go coloured and they make it smell of a nice fragrance like lavender or something like that. And so bath bombs contain citric acid, so this is an acid, and sodium carbonate. When they react, a gas is produced, and so that's why you get the bubbling as it goes in. Complete the word equation for the reaction that takes place. Citric acid and sodium carbonate make sodium citrate and water and another gas. And so we have to look at the words present on the left-hand side and have a think about what's missing. So we've got sodium in the reactants and we've got sodium in the products. That's already been spoken for and used. We've got the citric acid and we've got citrate there. And so the only bits that we have not had any mention of so far in the products is the carbonate. And that sounds very much like a gas that we know that's got carbon in its name, and that is carbon dioxide. And that's the right answer there. Now, this has a word equation as well, by the way, so I don't want you to write CO2 there, even though that is the formula of carbon dioxide. Now, the next part of this question involves an experiment. The bath bomb was dropped into hot water and its mass was measured every 30 seconds for 3 minutes. And this is a graph of the results. Now, I've deliberately got the question on the next page just so we force us to have a look at what this graph is showing. And so as we go to the right, time is passing. And so the experiment has been going on for longer. And what is changing over time is the mass. So this graph is showing us how the mass changes over time. And so what I hope you can see quite clearly is at the beginning, the mass is at its highest at 225, or just above it, I think, actually. And then at the end, it has dropped down to about here, which is about 5 or 10, something like that. So at a quick glance, what you can see is that the mass has definitely dropped. It's decreased a lot. And actually, it's decreased a lot more in the first half of the experiment than it does later on. So it drops a lot at the beginning, and then later the mass drops quite a bit less. Okay, now on to the actual question about the graph. Between which two times on the graph does the mass of the bath bomb decrease the fastest? And we're ticking one of the correct boxes. And so we've got between 0 and 30. So 30 is here on the graph. And so at 30 seconds, the graph is 3 squares above 125. Now each square, because there's 5 little mini squares, and between 125 and 150 is 25, that means each little square is worth 5. And so 125, 130, 135, 140. And so the mass is at 140 here. And at the beginning, I said it was about 225. It's actually one little square above 225, so it's at 230. And so in that 30 seconds, it's dropped down from 230 to 140. And so that is a decrease of 90. And then between 30 and 60, so here we are at 60, and the mass looks like it is at 85, I think. And so that means it's gone down from 140 to 85. So it's gone down by only 55 as a decrease. And we know that it's going down steeply at the beginning because we can see it's gone down by 90 and then it's gone down by 55, and it's definitely, the curve is getting more gentle as we go down. So the fastest decrease is the steepest part of the graph, which we can see now is between 0 and 30. The bath bomb was 230 grams at the start. Well, we'd worked that out, so that's good. How long does it take for the bath bomb to decrease by half? Now, 230 divided by 2 is 115. So the question is really, how long does it take for the graph to reach 115? Now, I'm just going to change my line to blue, just so it stands out against the yellow. So if 100 is here, that's 105, 110, 115 is 3 little squares up. And so if I move along from 115 and then I move down to my x-axis, we should find it's about, I make that about 43 seconds. And so that's how long it took for the mass to halve. But you are allowed, for a question like this, anything between 41 and 45. There is normally a range. It's definitely past 40, but it isn't past 45. And then finally, the reactants in a bath bomb were 176 grams at the start. 129 grams of sodium citrate and 14 grams of water are produced in the reaction. What is the mass of the gas? Now, one of the rules is that the mass at the start must be equal to the mass at the end, because you cannot just destroy atoms from nowhere. And so it was 176 grams at the beginning, and 129 grams of sodium citrate were produced, and 14 grams of water were produced. And so the answer for how much carbon dioxide is, we take away the two masses from 176 and we get 33 grams as our final answer, because that is 176, take away 129, take away 14. Okay, this is the final part of the final question. Some people on cruise ships practice golf. They hit golf balls into the sea. Turtles can swallow the golf balls. A new type of golf ball has been made from a bath bomb covered in hardened paper to use on cruise ships. Suggest one reason why this type of golf ball might be better for the environment than a normal golf ball. Well, think back to the experiment that we've just been doing. The experiment showed that the bath bomb reacts with water. And so when this golf ball, this new golf ball, gets wet, the chemicals will react and the ball will be destroyed. And so that's all that we need to say. When the ball gets wet, the chemicals will react and the ball will be destroyed. Alternatively, we could use, so this is an or, we could use the word biodegradable by saying they, and by that we mean the ball, are biodegradable. And so that means that they won't sit around for an animal to eat. They will quickly react with the water and they will break apart. That's what degrade means. It will break up naturally in the environment. We could also say that they will dissolve. It's not quite literally dissolving, but it is acceptable, and some of you might have put that in your answer. Now, you could come at this from the other way around. You could say that normal golf balls don't react, and so that implies that these would. But I think it's far better to say what these new golf balls will do. They will react. And therefore the products of the reaction, also worth noting, are going to be harmless. This very last question then, complete the word equation for the reaction between citric acid and calcium carbonate. Use the equation in part A to help you. Now this was the equation from part A. The citric acid reacted with sodium carbonate, and we just need to look first of all on the left hand side. The only difference between the equation in part A and the one now is that we're not using sodium carbonate, we're using calcium carbonate. So just like in part A, where sodium citrate was produced, well, we're going to make calcium citrate. So that is going to go in the first gap. And then last of all, just like before where you filled in that this was carbon dioxide was the other product, well, the other product would again be carbon dioxide. And both of these are required, because notice that there is only one mark up for grabs here. So unfortunately, you can't get half a mark here. You have to have both of them. Now, these could be in either order. It doesn't matter where you put them. You get the marks either way. So you could put carbon dioxide first in this space, or where it is, how I've shown it here. Okay, that's the end of the questions. Hope that was useful. I'll see you again soon.